I showed you that for a pendulum, the frequency and the period of oscillation don't at all depend on the mass. For a mass on a spring instead, like this one that bobs up and down when heavy weights are hanging from the spring, it very much depends on the mass. In fact, if we had the natural frequency for a mass on a spring, we see that the natural frequency denoted by F sub n is 1 over 2 pi square root of k over m, where k is the same spring constant that we found just a moment ago, and the mass is the mass that's hanging on this spring. So I have 4 different weights here for the mass. I have 4 different masses, 4, 6, and 8 kilograms, and we can do the experiment. And you can see that this formula shows that the mass appears in the expression for the natural frequency, which means that as you change the mass, you change the oscillation frequency, unlike the situation for the pendulum. So let's try starting from 4 kilograms. I'm going to do 10 oscillations of this. I'm going to displace it. You see that there are 4 kilograms now, and so this yellow bar indicates 4 kilograms. So on this thing, that's basically a scale, just like the scales you see at the market. Now, if I displace it, say for example to the position of 6 kilograms here, I stretch the spring, but the spring wants to restore the position, that's the restoring force, that's Hooke's force, and then this entire mass in spring system is going to start into its oscillation. Because of inertia, it's not going to stop at 4, it's going to keep on going up. Then gravity will slowly decelerate it until it stops at the top, and so on, and it will keep bobbing up and down around the rest position, the equilibrium position at 4, which is determined by this mass. So let's get started. I displace it at 6. I'm gonna start recording when it comes back down and count 10 oscillations from there. So go, start. 3, 4, 5, 6, 7, 8, 9, 10. 7.4 seconds. Let's try with, and if we go to the board, that's exactly for the 4 kilograms what I have measured before. I'm impressed with my own accuracy. 7.4 seconds for 10 periods t. And so for 1 period t, we have 0.74 seconds, and the natural frequency is the inverse of the period. Remember, the frequency is 1 over t, t equals 1 over f. And so the natural frequency with 4 kilograms is 1.35 hertz. If we plug in the numbers and calculate the natural frequency, assuming k is 272 newtons per meter and the mass is 4 kilograms, we obtain this number, 1.31 hertz. The two are very similar to one another, so within the measurement error, these are identical numbers, 1.35, 1.31 hertz. Let's repeat the experiment with a different mass, now this time with 6 kilograms, and see what happens. I add a 2 kilogram weight, I zero the timer, I see that this yellow indicator is at the 6 kilogram tick, and I'm going to displace it down to the 8th kilogram tick and let go. When it comes back down, I start, and then I stop at 10. So start, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.1 seconds. Previously, I had made a slightly different time. I had 9.3. It's all within the measurement error, so it doesn't really matter. This is what we get. And again, you can see that the measurement and the calculated frequencies are very similar to one another at 1.07, 1.08 hertz. Let's try with 8 kilograms. And we're going to get yet a third number. Why? Because the frequency of oscillation very much depends on the mass, unlike the situation for the pendulum. So let's try for 8 kilograms, and you see that the yellow tick is at 8, and I displace it to the 10th and start when it comes back down. So start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0.7. Previously I had 10.5. Same story within the error. These are similar measurements, and we end up with a slightly different measurement. We had 0.95 hertz, 0.93 hertz. So these are very similar again to one another, the calculated and the measured in this very experiment. So you can see that varying the mass very much varies the frequency of oscillation. And this is true for any mass on a spring, any different spring with completely different spring constants, of course. Thank you.